All right, here are the solutions to the accelerated motion practice. So, to begin with, we have a couple things that are just notes. So our definition of acceleration is when we have a couple things that we want to say, right? It's the rate of change of velocity. It's the rate of change of velocity. It's how quickly we're changing velocity. It includes speeding up. That's going to cause a change in velocity. It includes slowing down. And it includes changing direction. Oh, sorry, that's not very nice. Includes changing direction. Now, the other thing that's going to be really important for us today is that acceleration is the change in velocity over the change in time. So these are all the things that count for what acceleration is. Question 2, how can you tell when an object is accelerating by looking at the velocity versus time graph? Basically, you can tell that an object's accelerating because the velocity changes, or the graph is not a horizontal line. Both of those things indicate that the velocity has changed. And anytime that the velocity changes, like when we're speeding up, slowing down, or changing direction, anytime that happens, then we are experiencing acceleration. So, how can you tell when an object is accelerating by looking at a position versus time graph? This takes a little bit more work to do, but on a position versus time graph, on x versus t, slope is velocity. That's an important part of this whole thing. So if the slope on position versus time is velocity, an object that's accelerating acceleration is a change in velocity. That's our definition for acceleration. And yeah, I wanted to write that down again. So on position versus time, slope is velocity. Acceleration is a change in velocity. This means on x versus t, the slope changes. If the slope changes, that means the line is curved. That's what it means to accelerate on a position versus time graph. Anytime we see a curved line on position versus time, we are accelerating. How can the acceleration of an object be found from a graph of velocity versus time? Well, on a graph of velocity versus time, the slope of any graph is the rise of the graph over the run of the graph. On a velocity versus time graph, the rise is velocity, and the run is time. So the slope of that graph is going to be the change in velocity over the change in time. That's the acceleration. What we know here then is that the slope of velocity versus time is acceleration. That's really, really important. The slope of velocity versus time is acceleration. All right, number 5. For each of these graphs, we're going to find the initial velocity, the final velocity, and the time and the acceleration of the object. We're going to get all that by looking at the graph. So before we jump into that, there's something I want to talk about with these graphs just really, really, really quickly. So when we look at a velocity versus time graph, and a velocity versus time graph looks like this. First off, mathematically speaking, we have a math equation that we can describe any straight line with. Our math equation that we describe a straight line with is y equals mx plus b. That's the slope-intercept formula. That works for any straight line. That's our math equation for this. Y is the y value, x is the x value, m is the slope, and b is the y-intercept. We're very familiar with that. We're in physics. So we need to be able to translate from this math equation. So the translation is very important. So we get a math equation, but it requires some translation. Now, for our translation, all of the y values on the graph are different. And if we look over here, on this graph, all of the y values are velocity. So we're going to have y go from just being y, which is a placeholder, a variable, to something specific, velocity. The next thing we need to look at is the slope. Well, we just talked about this. The slope here is equal to the acceleration. Acceleration is an a. So that's how we're going to translate that. The slope is no longer m, a variable. It's something specific. It's the acceleration. And we have our definition for acceleration. We already wrote that down. The next thing we have is the x value. Looking at our graph, all of the x values are time. So we're going to translate that to a t. And then the last thing we have is the y-intercept. That's my y-intercept. But here, that y-intercept is a special kind of velocity. It's where we start. It's the initial velocity. So it's v initial. So when we do our translation from the math equation, when we try to understand what's physically going on with this, instead of y, we're going to write velocity. Instead of slope, we're going to write acceleration. Instead of time, instead of the x value, we're going to write time. And instead of the b for y-intercept, we're going to write the initial velocity. This is our physics equation. It's all the parts of the graph that you've done before in math, but we've translated it from this general parent math equation for a straight line into a physics equation where we've given every single piece of that math equation a physical meaning. And so here, this is one of the things that we can use as we talk about this. So all the things that you've ever done with the graph, you can still do with this graph. We're just going to change the names of stuff because we want it to mean different things. So let's go through here. And then let's look at what that means on each of these problems. So for the first one, we're going to find our initial velocity. I know that's my y-intercept. That's right here. So for A, the initial velocity is 15 meters per second. And then we end down here, that's my final velocity. I'm going to get all my velocity values from the y part of the graph. So if I want my final velocity, it has to come from the y-axis. That's going to be negative 15 meters per second. I'm going to get information about time. That's going to come from the x-axis. So what I see here is that my whole motion takes place with a time of 20 seconds, and then I need to calculate my acceleration. So the acceleration is the change in velocity over time. My velocity goes from positive 15 all the way down to negative 15. That's a change in velocity of negative 30 meters per second, and it takes place over 20 seconds. So my acceleration is negative 1.5 meters per second squared. Let's do this again on part B. My initial velocity starts right there. It's my y-intercept, and so my initial velocity is negative 2. My final velocity, when we end over here, we read back from the y-axis because that's where my velocity information is. My final velocity, sorry, -2 meters per second, is -4 meters per second. The time that the entire thing takes place in is again 20 seconds. And then we need to calculate our acceleration. So the acceleration is the change in velocity over the change in time. If we go from -2 to -4, my change in velocity is -2 meters per second, because that's the distance between 2 and 4, but it's going down, divided by the time of 20 seconds. So that acceleration is -1 meter per second, sorry, not -1, -0.1 meters per second squared. Continuing on, here we have a different kind of line. Here we have a positive slope. And since it's velocity versus time, that means we can expect to have a positive acceleration. So let's see if that comes out when we analyze this. Looking at my intercept, it looks like we start off at 0, so the initial velocity is 0 meters per second. And then when we end, final velocity is way up here. That's 50 meters per second. The time that this whole thing takes place in, the time is all the way out to here, 15 seconds. So if we calculate the acceleration, that's the change in velocity over the change in time. So we start off at 0 and we go up to 50. That is a positive change in velocity. We've gained some speed. So that's 50 meters per second divided by the time of 15 seconds, giving me an acceleration of positive 3.3 meters per second squared. Looks like a 5. 3.3 meters per second squared. And it's a positive acceleration, which is what we expected with a positive slope. Now, over here, all my value for velocity starts off negative, but I still have a positive slope, so I should have a positive acceleration. Well, let's go through it. We start off here with an initial velocity of -40 meters per second. And I end up here with a velocity, final velocity, of 20 meters per second. And the time that that whole thing takes place in is 15 seconds. So if we're going to calculate our acceleration from this, it's the change in velocity over the change in time. When my velocity goes from -40 all the way up to 20, that change in velocity is positive 60 meters per second divided by a time of 15 seconds. So that comes out to be positive 4 meters per second squared. That's how we would get acceleration from a velocity versus time graph. We're going to find the slope of that straight line. So here we've got some problems, and it's going to throw some wrinkles into what's going on, or at least what we're used to. So let's go through it. And again, for word problems, we're going to use a really simple little text analysis thing. We're going to box our given data, and we're going to circle our unknown. That's how I want us to go through problems. Right now, we're just going to box our given data and we're going to circle our unknown data. So let's go through this first one. An object accelerates from rest to 70 meters per second in 3.5 seconds. So I've got 3 pieces of information right away. Then I want to know what is the acceleration of the object. So my givens, rest, and it says accelerates from rest. That means we start off, we have an initial velocity of 0. Because when something is at rest, the velocity at that time is 0. And then I go from rest to a final velocity of 70 meters per second in a time of 3.5 seconds. And my unknown here is the acceleration. Well, the one of the equations that we have right now is acceleration is change in velocity over time. So if I go from 0 to 70, my change in velocity is positive 70 meters per second in a time of 3.5 seconds. That gives me an acceleration of 20 meters per second squared. For the next one, we'll change our color scheme. An object is traveling at 5 meters per second. It then stops in a period of 10 seconds. What's the acceleration of the object? So, my givens, it is traveling at 5 meters per second, then it stops. So that means my initial velocity is 5 meters per second. If it then stops, my final velocity, if we stop, that's another case where that final velocity is going to be 0 meters per second. Rest up here means 0 meters per second velocity. Stops also means 0 meters per second of velocity. And then my time here is 10 seconds. We're going to use the same equation. Acceleration is the change in velocity over time. If I go from 5 to 0, I'm losing velocity. I'm not gaining it. So my loss in velocity makes it negative change in velocity, 5 meters per second. We took that velocity away, divided by 10 seconds. So this acceleration comes out to be negative 0.5 meters per second squared. Just 3 more. These go quick. An object traveling at 8 meters per second speeds up to 12 meters per second in 2 seconds. So it's traveling at 8 meters per second. It speeds up to 12 meters per second in 2 seconds. What is the acceleration of the object? Is traveling, that tells me that the initial velocity is 8 meters per second. It speeds up to, so the final velocity is 12 meters per second. And the whole thing takes place in a time of 2 seconds. And what we're after here is the acceleration. The acceleration is the change in velocity over time. I go from 8 meters per second to 12 meters per second. My change in velocity is 4 meters per second. It takes place in 2 seconds, so my acceleration is 2 meters per second squared. All right, last one. An object traveling at 22 meters per second slows down, not our last one, sorry, to 12 meters per second in 5 seconds. What's the acceleration of the object? Okay, so my givens are that we are traveling at 22 meters per second. So if we're starting off that way, that's our initial velocity moving at 22 meters per second to a final velocity of 12 meters per second. And it's doing all of this in a time of 5 seconds. So if we want to find the acceleration, it's going to be the change in velocity over time. My change in velocity, we go from 22 down to 12. That means my change in velocity is negative 10 meters per second in a time of 5 seconds. That makes the acceleration negative 2 meters per second squared. Last one. An object traveling at negative 4 meters per second has an acceleration of 8 meters per second squared for 3 seconds. What is the final velocity? So if we look at this, here's a quick way that we can do this if you're not a fan of writing everything out like this. An object traveling at 4 meters per second, that is my initial velocity. Has an acceleration of 8 meters per second squared, that is my acceleration for a time of 3 seconds. That's my time. I want to know the final velocity. So my givens, the initial velocity is negative 4 meters per second. My acceleration is 8 meters per second squared. My time is 3 seconds. And I want to know, my unknown is the final velocity. Now, here are my choices for equations. Here are my possible equations. It could be acceleration is change in velocity over time, or the other one, the one that we got from the y equals mx plus b equation, is that final velocity is equal to acceleration times time plus the initial velocity. So if we look at that, I'm looking for final velocity. That's going to be my easiest choice. So let's plug everything in. Final velocity is acceleration 8 meters per second squared times the time, 3 seconds, plus the initial velocity of -4 meters per second. When I multiply seconds and meters per second squared, meters per second squared means that the seconds are in the denominator. So seconds and seconds squared cross out. So I have 8 times 3 meters per second, 24 meters per second, minus 4 meters per second. My final velocity comes out to be 20 meters per second.